Good morning. Today is February the 10th. This is World Regional Geography, 1010, Section 98B. And today we have several things to cover. First is a simple housekeeping note or two. And let's see, we get to 98B here. So the first housekeeping note is to just be aware that there is a writing assignment due. Writing assignment 3 is due on Monday, and just be aware of that. And so be aware of the fact that the writing assignment instructions are here at this link, and then the writing assignment reading materials are at this link. So don't get confused. The instructions are also posted here just for your own edification. The Dropbox is at the other link. So just be aware of that. Also note that the lecture recording from Monday is here. I also emailed it to you all. Also, the Unit A exam, I am going to go ahead and say that it will be administered on the 24th of February. The format will, wait a minute. I'm not sharing my stuff. I thought I started sharing the screen. Okay, let's try this again with the screen up. Sorry about that. Okay, so again, we have you have one writing assignment due on Monday. So the instructions for the writing assignment are at this link. Just be aware of that, and that the instructions are also posted at this link, along with the readings that go along with the assignment. So I talked about that assignment in detail on Monday. Just wanted to remind you that you do have that writing assignment due. There's the lecture recording that is due on, well, the 15th also, but you should watch it as soon as possible so that if you have questions, you'll be able to ask intelligent questions and helpful questions. And last but certainly not least, as I started to say earlier, I am going to announce 2 weeks in advance that your Unit A exam will be administered on February the 24th. And so you will have a few days to get it done. You'll download it from here in Word format. It will be a multiple choice exam, I believe 50 questions covering Unit Exam A, which includes the history of geography timeline, also includes the lecture today, map interpretation basics. It includes everything that we have been discussing with associated with Unit Exam A. So that will be 2 weeks from today. Just letting you know that in advance. If you have any, and there will not be someone asked about a exam review. It's an open book exam. So, there's no need for a review sheet for an open book exam because everything will be in front of you. You will have plenty of time to get it done. So it won't be an exam that I release for 1 hour and you've got to try to get it done in an hour. It's not going to be like that. It's going to be open book. It will be to your advantage to watch the videos and do the reading ahead of time so you're not trying to juggle your exam and all of your other work from other classes at the same time that particular week. So it's good that you are here and watching the recordings. Okay, so let's jump into our lecture today. Last time we started off looking at the concept of map interpretation, obviously a very important concept in geography. And so we started off looking at the map interpretation basics document, and we covered we talked about the importance of time and date on maps. We went into a little exercise and discussion on directional orientation, and we talked about the 3 types of map symbols. And so today we are going to start off with the concept of location. And so with location, we're going to, of course, begin by looking at latitude and longitude. And so latitude and longitude, the latitude longitude grid system is how we quantitatively locate places on the Earth's surface. And latitude and longitude comprise what we call absolute location. And so absolute location is very important for obvious reasons that we've discussed over and over. So let's talk about latitude first. So latitude is the arc angle distance north and south of the equator, measured in degrees. And so if we go from 0 degrees at the equator north to the North Pole, that maxes out at 90 degrees north. And of course, 90 degrees south is at the South Pole. And so you might be thinking degrees. Why degrees? So remember the last time we talked on Monday or had class, I mentioned that geometry, geo-earth, meter, to measure, means to measure the earth, while geography, geo-earth, graph to describe, means earth description. So there's a lot of geometry involved in geography. And so when we talk about a right angle, this is a 90-degree angle. So if we start off at the equator at 0 degrees and we go to the North Pole at 90 degrees, so we're actually measuring the distance along that curve of the Earth that goes from the equator to the North Pole, and of course, conversely to the South Pole. So that's where we get the degrees from. And so a degree of latitude or longitude is actually measuring a distance along the surface of the Earth. Now, each whole degree of latitude is about 69 miles. And so if you are reading or have read, it says here, the degree of one latitude, the length of 1 degree of latitude, therefore, is 111 kilometers or 69 miles, which is most familiar to us. Okay, so that varies for longitude somewhat. So obviously latitude is defined, or at least 0 degrees latitude is a logical starting point. It is the equator. The equator is a circle. The equator, in fact, is a great circle, but it slices the Earth in half, or it bisects the Earth, and that circle is perpendicular to the Earth's axis. So the Earth rotates on its axis. So the equator has a pretty logical quantitative definition. What about longitude? Well, longitude obviously is based upon the distance east and west of the prime meridian measured in degrees. The prime meridian is 0 degrees longitude. So notice that unlike the equator, there's only one great circle that slices the Earth in half, and is perpendicular to the Earth's axis. Now, the prime meridian is a great circle that slices the Earth in half and goes through both the North and South poles. There are an infinite number of there's an infinite number of great circles that do that slice the Earth in half at the and pass through the poles. So the question is, well, how do we get to decide zero? Which one is zero? I mean, there's no definitive quantitative designation for that. So the decision for which great circle is 0 degrees longitude, of course, was decided by humans, as is described in this paragraph here, and it says that in 1884 there was an international meeting that designated the prime meridian as passing through the Greenwich Observatory on the outskirts of London. And so if you might be asking, well, how can we figure out where that is? Where is the prime meridian? You know, we can always locate the equator, no problem. Locating the equator. Prime meridian, we'll use this Mercator projection. Actually, what I'm going to do is I'm going to go to the reading assignment, the map that's included in the reading assignment, because it's much easier to read. So here is 0 degrees longitude. Notice there's Great Britain, and there's England, and there's London, England. And so if you see that line, that is the prime meridian. And so we go from 0 degrees west to 180 degrees. This is the Western Hemisphere. And then on the other side, we go east to 180 degrees. 180 degrees east-west is also known as the international date line. And so from 0 degrees longitude east is the Eastern Hemisphere. That's how we define the Earth's hemispheres. So when we describe latitude and longitude and put them together, then we use them, of course, to find locations on Earth, or what we would call absolute locations. And so absolute location is latitude and longitude combined. So now we're going to go through a little exercise to show you exactly how the latitude, longitude grid system works. And you're going to be introduced to 2 grid systems that are really the same, but have different utilizations. So we're going to start off with the degrees, minutes, seconds system. So what does that mean? So what you see here, this 39 degrees, 22 minutes, 18 seconds, is a location on the Earth's surface. So it's 39 degrees, 22 minutes, 18 seconds north latitude, 76 degrees, 38 minutes, 5 seconds west longitude. Okay, so the question is, well, where is that? Or how is this used to determine location? So remember what we learned a couple of seconds ago, is that each whole degree of latitude is about 69 miles. Okay, so if we were to limit ourselves to just the whole degree, we would say this point on Earth is at 39 degrees north, 76 degrees west. If we were to limit ourselves to that level of accuracy, so that gives us a 69-mile level of accuracy, right? But obviously, we might want to have a greater degree of locational accuracy, right? Now, if we were trying to locate a country and we said, well, this country's at 39 degrees north, 76 degrees west, that might be good enough. But what if we were trying to find a city within a country? Could we say, well, this city's at about 39 degrees north, 76 degrees west? We could be off by 69 miles. Now, if we were flying an airplane or in a spaceship where we could see from above, that might be okay. But if we're driving and we're 69 miles away from the location that we're trying to find, the whole degree is not good enough. So let's break the whole degree down into 60 minutes. So each minute of latitude or longitude is approximately 1 mile, about 1.1 mile, 1.1 mile. So if we're looking for a city, most cities are larger or wider than 1 mile. If we're looking for a city and we say there's a city at 39 degrees, 22 minutes, 76 degrees, 38 minutes, 39 degrees, 22 minutes north, 76 degrees, 38 minutes west, then we should be able to find that city. But in most cases, we're not just trying to find the whole city. We're trying to find a specific location in a city. So let's say when you were on your way for the first time to Tennessee State University, and let's say you were coming from out of town, getting within a 1 mile radius or having a 1 mile level of accuracy to Hale Hall or the university apartments, that's not good enough. I mean, a mile away from Tennessee State University's campus, if you're driving around and you have no idea where you are within a 1 mile level of accuracy and you're trying to find a specific building, that's not good enough. But what if we break each minute into 60 seconds, right? So now we say that the location is at 39 degrees, 22 minutes, 18 seconds. Each second is about 100 feet. So if you're driving, if this is the lat long you're given, or some of the lat long that is down to seconds or within 100 feet of accuracy, and you get within 100 feet of Hale Hall or Rudolph Hall, you should be able to see it. Okay, so that's how the degrees, minutes, seconds system works. Let's do a little exercise. Just did it for the last class. So what we're going to do is I'm going to illustrate how this degrees, minutes, seconds system works with Google Maps. So here's 39 degrees north, 76 degrees west. So that gives us a location somewhere in Maryland, actually on the Delmarva Peninsula. It's the Delaware, Maryland, Virginia, Delmarva Peninsula. So a peninsula is a piece of land that is surrounded on 3 sides by water. So that's why this is called the Delmarva Peninsula. Okay, so but is that the precise location that is represented by this, oh, for God's sake. Sorry. That's represented by, I gotta be real careful, by this latitude, longitude? No, it's not. We want 39 degrees, 22 minutes, 18 seconds. But let's take this, let's say 39, 22 minutes here. I think it was 70, real careful here, 38 minutes there, 76 degrees, 38 minutes, and boom. So now notice we are at a different location. So when we were within 69 miles of accuracy, we were somewhere over here on the Delmarva Peninsula. But now that we've gotten more accurate, then here we are. So again, this is the importance of breaking each whole degree down into minutes and seconds. So if we were looking for, say, Baltimore City, and we only had the whole degree, we were way over here somewhere. We were like, well, we know it's around here somewhere. Now we can clearly see where Baltimore is on this map, but if we were driving on the ground, we would have a hard time trying to figure out how to get here from here, right? But when we add the minutes in, now we're closer to where we're trying to go. But we're still not quite there exactly. We still are not in the exact location. We're off by about a mile or so. So we add in the seconds, 18 seconds and 5 seconds. Now we're going to get exactly where we're going to go within 100 feet. Okay, so where are we trying to go? Well, here's the location, the Boys Latin School of Maryland. So perhaps some parents were trying to visit this private school to see if they're, I think this is an all-male school still, maybe, I don't know. Now they're there. If they get within 100 feet of the school campus, they should be able to find it, okay? Now, if you notice, we have the degrees, minutes, second system here for absolute location, but beneath it, we have decimal degrees. So notice the decimal degrees do not include the degree symbol. They don't include the little tick mark for minutes. They don't include the N for north or W for west. And so, well, why is that? Well, the reason for that is we cannot do mathematical computation with all these symbols involved. So we have to have just numbers, just numerals, and of course the minus sign. So this minus sign is how we show that a point is in the Western Hemisphere. So if you think about it, if we go back to the portion of the reading assignment that I referred to earlier, and I have to go all the way back to it, and we pull the Mercator projection map from this reading assignment, scroll down. So here's the Mercator projection map. Notice that the latitude, longitude grid system looks like an arithmetic grid, right? So if you're on it with an arithmetic grid with an X and Y axis, any number left of 0 is negative. So conversely, any number, any distance in longitude west of the prime meridian is going to be a negative number. Okay, so that's where that comes from, in case you were wondering. And so that's why this 76 degrees west translates into minus 76 degrees. Well, really, it's 76.63, so on and so forth. So you might be wondering about that. Okay, so what do all these numbers past these decimals mean? Why is that there? Why don't we just round these numbers off? Why isn't this just 39.37 and negative 76.63? Certainly we could round the numbers off. However, we would lose locational accuracy if we do that. So notice we have 39.3 7 hundredths, thousandths, 10 thousands, 100 thousands, millions. So if we go six places after the decimal, we're breaking down that 69-mile arc distance into a million pieces. So if you take 69 miles and divide it by a million equal parts, you wind up with about 4 inches, right? So now if we go down to a level of accuracy represented by these decimal degrees, we can get down to about 3 or 4 inches of accuracy. And that's the kind of accuracy you need if you're going to be launching a satellite guided missile at a specific target, for surveying property. Surveying property, you can't be off by a few inches. That has to be exact, okay? For architectural renderings, I mean, those are the types of examples where you really need to have that fine level of accuracy. So that is how we use this system in order to determine locations on the Earth's surface. Now, one more thing I wanted to mention about location. When we use latitude and longitude, that refers to absolute location. So absolute location is when we use latitude and longitude to determine a location on the Earth's surface. Now, there's relative location. Relative location is where one place is relative to another place. And that's very subjective and qualitative. So let me give you an example. If you were to ask somebody in New York, how far is it, say, from wherever you were in New York to the Empire State Building, they might say, oh, it's right down the street, right? So in New York, right down the street might mean 10 blocks, right? Now, if you were in Texas and you ask somebody in Texas how far right down the street is, that might be 50 miles because Texas is a larger area. So that qualitative definition of location that is relative can't be used in scientific or spatial analysis because it's just very subjective. So that's the difference between absolute location and relative location. Now, I know this might be somewhat confusing, perhaps mystifying, but next week when we start to actually use geographic information system software, when you get your hands on the software and you're able to engage with the software and actually use latitude and longitude in a hands-on activity to solve a problem, then it'll make a lot more sense. Right now, it's kind of abstract. You're probably like, I don't understand this at all. But trust me, when you start using the software and start using latitude and longitude for a specific purpose, then it'll click for you. So if you're kind of fuzzy right now, don't worry, you'll catch on later. Okay, so we've looked at date, location, directional orientation, symbols, and now the next thing that we'll look at is map scale. Again, map scale is a concept that it might take you a little while to grasp. Well, what is map scale? A map scale is the ratio between distances on the map and corresponding distances on the Earth's surface, or the size of objects on the Earth's surface. So a map is actually a shrunk down version of somewhere on Earth. The question is, well, how much shrunk down is it? Is it 100 times smaller than the Earth? Is it 1,000 times smaller than the Earth? Is it 1,000,000 times smaller than the Earth? And so there are different ways to use maps so that we understand the relative size and distance. So there are three kinds of map scale. So the first type I'm going to introduce, well, not introduce you to, you've probably seen these before. These are graphic scales. These scales, and you've used these before. If I go back to Google Maps, you'll notice that on the map, on the far left-hand corner here, whoa, is the graphic scale right there in the corner. This one says 1 mile. So that distance on this map is 1 mile. Okay, whatever that distance is, that's 1 mile. So that gives you an idea of how far places are from one another, or how, so for instance, if you had a hiking map and you use the graphic scale and you measure the path along the trail on the hiking map with the graphic scale, and you noted that the trail that you planned on hiking is 6 miles from start to finish, you might reconsider that, because maybe you weren't planning on walking 6 miles. Maybe you thought we're probably going to do about 3. So perhaps you might decide with your hiking group, well, let's just go about halfway and then call it a day, right? But what we would not want to do is look at a hiking map or hiking trail map, not know how far the trail is, start hiking, get tired, and then realize, oh man, we got to walk all the way back. We're not going to be able to make it to the end of this trail. Now we have to turn around and walk back. Now we're tired. Maybe somebody's too tired to keep going. Now what? Now you're stuck somewhere in the middle of the woods. So the graphic scale, I'm sure you've all used that before. That's a very common scale, probably not new to you all for the most part. Okay, so that's one type of map scale. The second type of map scale that you may or may not be familiar with is the representative fraction. So the representative fraction is literally the ratio between the map and distances on the map. Distances on the map and distances in the real world. So your first representative fraction scale that is listed here is 1 to 63,360. So in other words, this means that any distance on the map is 63,360 times smaller than it is in the real world. So why is this 63,360 numbers kind of important? Well, if you scroll down, if you read, notice there are 63,360 inches in 1 mile. Okay. So what this means is that any inch of distance on the map that has this representative fraction scale represents 63,360 inches in the real world. Now, before you found out a few minutes ago that there are 63,360 inches in 1 mile, if I told you, well, this map has a representative fraction scale of 63,360 or 1 to 63,360, that probably wouldn't mean anything to you. Okay, well, and okay, what does that mean? But if I was to tell you that there's 63,360 inches in 1 mile, now you say, oh, okay, so what you're really saying is 1 inch on this map equals 1 mile in real space. Aha. So what I've done is described the verbal scale. So that's the second third kind of map scale is a verbal scale. So the verbal scale is used to simplify the representative fraction scale. Because like I said, if I was to tell you I have a map of 1 to 63,360 and you didn't know that there was 63,360 inches in 1 mile, you would have no idea what that meant, what the significance of that is. But once you break it down and say to a person, oh, 1 inch on this map equals 1 mile. Okay, yeah, I get that, right? Let's look at another example of translating a representative fraction into a more easily understandable verbal scale. So here we have, so let's say you have a map that's at a scale of 1 to 24,000. So on a map that has a scale of 1 to 24,000, that means that 1 inch equals 24,000 inches. Now, for most of us, even if I told you, well, 1 inch on this map equals 24,000 inches, could you really visualize 24,000 inches? I mean, there's certain distances that inches really don't work for in terms of measure. Just 24,000 inches, I don't know. But what if we were to divide that 24,000 inches by 12? Now I can say, well, 1 inch on this map actually equals 2,000 feet. That's a little bit better. Not perfect, because you still might not be able to visualize 2,000 feet. But if I give you another fact, which is that there are 5,280 feet in 1 mile, now you get a better idea. Most of us know about how far a mile is, either through driving or hiking or walking or running around a track. We kind of have an idea of how far that is, right? So we know that if there are 5,280 feet in a mile, and I tell you on a map that 1 inch equals 2,000 feet, then you know that that inch is a little bit less than half a mile. Now you kind of know how far that is, right? So if your hiking map, instead of being at a scale of 1 to 63,360, and I'm telling you right now, there aren't a whole lot of maps that are at that scale, but there are a lot of maps that are at 1 to 24,000 scale. Now you know that every inch on that map equals 2,000 feet. So 2 inches is almost is short of a mile. 3 inches is a little bit more than the mile, 6,000 feet. So you know that every 3 inches on the map, on that map, is a little bit more than a mile, and you can use that verbal scale to decide how far you're going to hike in that case. So again, map scale is not an easy concept to grasp at first. If we go into the textbook, and let me walk back a little bit just in case we have folks who have not yet accessed the ebook. I just want to walk this back a little bit. So you would start here and click here, and then that gets you to the ebook here. And so let's say you wanted to study or for the unit A exam about scale. So you would type scale here in the search bar, and then you'll get some search results. Now, you get lots of definitions here, and then you can click on the first one. Now, of course, you don't see scale right away. The best thing to do is to start scrolling. And as you can see, a lot of the concepts that we have discussed earlier are also here. Latitude, longitude, et cetera, if this gives you a better idea of what those concepts are. Oh, now here we are at map scale. And so let's look at this diagram here in chapter 1. So here we have 4 maps. We have a map of downtown Boston. We have a map zoomed out of the area around Boston, zoomed out a little farther, and then zoomed all the way out to include Boston and various surrounding parts of Massachusetts. Now, the map that is zoomed in on downtown Boston, notice, is described as a large scale map. So there are there are different types of representative fraction scale. There's large scale, and then there's small scale. Well, what's the difference? Just for your own basic edification for now, let's say that large scale maps, or maps that have large scale representative fractions, such as 1 to 25,000, 1 to 24,000, 1 to 1,000, 1 to 300. Those are large scale maps, and they cover relatively small areas. Okay, so large scale maps cover small areas. Notice that when we zoom out to a much larger area around Boston, now you notice that we have small scale representative fractions for larger maps. If we were to zoom all the way out to the entire United States, that scale might be 1 to 3 million or 1 to 5 million. Okay, a larger area is a smaller scale map, right? Smaller representative fraction scale. Now you might ask yourselves, well, how come 1 to 25,000 is large and 1 to 1 million is small? Well, what this really is a representative fraction. So this is actually 1/25,000th, and this is 1/1,000,000th, right? So this map is 25,000 times smaller than the area it covers. This map is 1,000,000 times smaller than the area it covers, okay? Simplifying it further, if you had a pie and you sliced that pie into 25,000 pieces, and you took that exact same pie and sliced it into 1,000,000 pieces, obviously one of those 25,000 pieces is going to be larger than the slice that is one of 1,000,000 slices, if it's the same pie, right? So that kind of hopefully will give you a better understanding of map scale. So we've discussed map scale. You should read more about map scale. We've talked about cartography, so on and so forth. But let's go back to look at latitude specifically from a deeper perspective. And so we have to go back into the reading assignment. Again, that covers a lot of geography basics, a lot of vocabulary that you should examine for unit exam A. But it also includes these various lines of latitude, such as the Arctic Circle, which is at 65.5 degrees north, the Tropic of Cancer, which is at 25.5 degrees north, the Tropic of Capricorn, which is at 25.5 degrees south, and the Antarctic Circle, which is at 66.5 degrees south. So what is so special about these various lines of latitude? Well, the Tropic of Cancer and the Tropic of Capricorn represent the northernmost latitudes and the southernmost latitude that receive the sun's direct light throughout the year. So if we go to this diagram here, this somewhat illustrates what happens. So as the Earth revolves around the sun, its axis is not perpendicular to the plane that slices the sun in half. Okay, so here's some more geometry. So there's a plane that slices the sun in half, okay, within which the Earth revolves around the sun. The Earth's axis is not perpendicular to that plane. The Earth's axis is actually tilted 23.5 degrees away from the perpendicular to that plane. In simple terms, as the Earth revolves around the sun, it maintains that tilt. And what happens is the Earth receives different amounts of sunlight at different places at different times of the year. And that's what causes the seasons to change. Because it's not that the sun is close to the Earth or farther away from the Earth. No. Now, there are points of time of the year when the sun is closer to the Earth and farther from the Earth than others. Because as the Earth revolves around the sun, it is not in a perfect circle. And the sun is not at the center of that circle. But that's a whole other discussion. But in any case, that offset between the Earth and sun and as it rotates annually, as it revolves around the sun annually, has nothing to do with the change in seasons. It's this tilt. Okay, I can probably show you better. There's a much better diagram here in the other document. So here's a schematic diagram. These arrows represent the sun's direct rays, okay, or the sun's rays. But notice that on the summer solstice in the northern hemisphere, which is represented by this diagram, notice here's the Earth's axis, North Pole, South Pole. Notice the Earth is tilted. It's almost like leaning into the sun. Here, the sun's direct rays on that particular day. And so if you notice, the sun's direct rays are directly above the Tropic of Cancer on the first day of summer in the northern hemisphere. Look at the illumination. Notice that most of the northern hemisphere is experiencing daylight. Most of the southern hemisphere is experiencing night. So now when we get to areas north of the Tropic of Cancer, they do get sunlight, but there is no contact with the sun's direct rays north of the Tropic of Cancer, ever. So we go to this diagram. So here's the Tropic of Cancer. Now to orient yourself on the Earth's surface, here's the Tropic of Cancer at 23.5 degrees north latitude. Notice that the conterminous United States, that's the 48 states here, no direct sunlight ever, no direct sunlight in Canada, not Alaska. The only place in the United States that, the only United state, we do have territories that are in the tropics, is Hawaii, right? The rest of us, we never received the sun's direct rays. So the region of the Earth known as the tropical region has a quantitative definition. It is the portion of the Earth that is between 23.5 degrees north and 23.5 degrees south that receives the sun's direct rays at some point during the entire year. And so as we get farther into the course, you'll notice how that affects the seasons. So in our part of the world, we have 4 seasons. One of them is winter. And we have winter because there's a deficit. Let's go over to this other part of this diagram. So this side, on the right-hand side, is the first day of winter in the northern hemisphere. Notice that the northern hemisphere is, most of the northern hemisphere is dark. Notice that north of the Arctic Circle, there's no light at all, 24 hours of darkness. Conversely, the southern hemisphere, when it's their summer, their first day of summer, the areas south of the Antarctic Circle experiences 24 hours of light. Sun never goes down, and after that, it really doesn't go down for a while. There's lots of light. during that time of year in the Southern Hemisphere. So these lines of latitude that we deem important are directly associated with the relationship, with the geometric relationship between the Earth and the Sun as the Earth revolves around the Sun. So you should make note of that. You should make note of the significance of these lines of latitude. You should know where they are. You should know where these lines of latitude are relative to land masses, specifically the land masses that we're studying right now. So you should know approximately where the contemporaneous United States is. You should know approximately how far west Alaska is versus how far east uh, the east coast of the United States is, and so on and so forth. Because you will be asked to determine the landmass or place associated with specific latitude and longitude. So right now you should have a general idea. So for example, if I ask you at some point, perhaps on an exam, if a point at 45 degrees east, 23 and a half degrees north is in the United States, you should know immediately it's not, just due to the fact that it's 45 degrees east. That should be like, no, that can't be in the United States because first of all, it's in the Eastern Hemisphere. So those are kind of questions that you will be asked. You'll need to be able to orient your location on the Earth's surface during an upcoming exam. But once we start working with geographic information systems and you start using it in practice, the Earth, locations on the Earth will become a lot more familiar to you in time. Okay, whoops, let's see, where are we? We have looked at, I think we have looked at date, location, directional orientation, map symbols, map scale, so on and so forth. Last but certainly not least, let's be sure that we have that we're familiar with the various terms. So we've talked about direction, yes, absolute location, yes, latitude, longitude, yes, map scale, 3 kinds of map scale, ISO lines, here are the various ISO lines, we've already talked about those. Topographic map, we know what that is. Now, a choropleth map is a map that uses color area symbols to convey a message to the map reader. So a choropleth map uses color area symbols. Remember, there are 3 types of map symbols: point, line, and area. So a map that uses color area symbols, and I've showed you a couple of those earlier, that's called a choropleth map. We've also discussed GIS, remote sensing, global positioning systems. Now, generalization. So for generalization, I'll take you back to this textbook. Generalization is when a cartographer leaves features off of a map so the map is not cluttered. And so let's look at this first map that includes downtown Boston. Notice you have building footprints. Notice there are all these streets, but when we zoom out, notice now you only have City Hall. The rest of these buildings are not there. On this second map at B, notice that the commercial street is still there, but it's not labeled. But all these other streets are not there. When we zoom out even further, now there are no streets, no building footprints. Those features are missing. And of course, when we zoom all the way out, we just have a point symbol representing Boston. So why does the cartographer, or why do we leave some of these features off of maps as we change scale? Imagine if we didn't. Imagine if all of the little streets on this map were still there. This map would be extremely cluttered. It would be very difficult for most human beings to read. most of us can only interpret 3 to 4 layers on a map, say a street layer, a point layer, maybe an area layer, a color layer. That's it. Once we get beyond 3 or 4 layers and there's 6 and 7 layers, we just get lost. We can't read the map. So that's why generalization is done. It's a purposeful uh, decision to leave certain features off of maps so the map can be easier to read. And so that is the definition of generalization. So that pretty much covers map interpretation, and we'll be doing map interpretation throughout the entire class. I mean, this is a geography class. This is just an introduction to map interpretation, just to give you the baseline knowledge that you need to go forward so that you'll be able to read maps that we examine for the rest of the class. So I am now going to stop the recording. And so I'm going to stop recording now. So again, for those of you watching this recorded lecture, again, if you have any questions, let me know. For those of you who are here,